1, 2점 때문에 그레이드가 내려가는 친구들이 꼭 있어. 한 5명씩은. 그래서 숙제도 최대한 성의를 보여서 내셔야 됩니다. 스몰 디퍼런스 때문에 그레이드가 레터가 바뀌는 경우가 없게. 그렇죠? 그러면은 이어서 시작하도록 하겠습니다. Okay, let's get started. Today we'll study about the delocalization. We're getting into the new chapter. And this is an announcement for homework 1. Okay, so last week the result for homework 1 grading is also announced on ETL, so you guys can double check your score and come to visit 7:08, 5 to 7 p.m. today and tomorrow. Okay, so students with ID Android odd numbers, right? You can visit 7:08. 5 to 6 p.m. today and 6 to 7 p.m. tomorrow. And students with ID number ends with the even number, they can come to visit 708, the same locations, 6 to 7 p.m. for today, 5 to 6 p.m. for Tuesday, tomorrow. Okay? 그래서 숙제 점수는 TA들이 후하게 준 편입니다. 그래서 그래도 혹시 모르니 점수 한번 확인도 할 겸 그레이드된 거 한번 확인도 할 겸 시간 되시면 확인하시면 될 것 같습니다. 그래서 장소가 다릅니다. 중간고사 때랑 758, 7층, 885로 방문하시면 돼요. TA 3명이 확인을 도와줄 것입니다. 다 안 된다. 월요일, 화요일 이 시간 정말 안 된다. 그러면은 TA에게 이메일로 연락을 주고 약속을 따로 잡아서 한번 진행을 하시면 되겠습니다. Okay? Right, that was the announcement, and I guess we couldn't finish the arcane chapter. I guess we have to deal with the last 2 or 3 problem set, designing a synthesis. I guess we covered this example, how to make this epoxide from this arcane, the simplest possible arcane molecules, and I guess this is the retrosynthetic and synthetic pathway, right? And we discuss about the retrosynthetic means. You can think about the step and backward. Right? So to make this, you can think of this olefin as a backward step. Right? In other words, you can think of then the oxidation from these substrate to synthesize the final product, and then you can go back one step further. To make this olefin, you can think about these alkyne, and then using the hydrogenation condition we studied, right, in the alkyne chapter, you can make this alkene from alkyne to make this cis product. We perhaps need a surface catalyst with somewhat deactivated form, so as to make and stop the reaction at alkene stage. Right? So you can think of then lindolar catalyst. And then to make this internal alkyne, right? You can think of the terminal alkyne, and we learn about deprotonation and alkylation step, right? From which you can make from this, this internal alkyne from this terminal alkyne, and also this alkyne can be made from the simplest possible alkyne, the starting material given in this problem. So we can then start with this alkyne, simplest possible alkyne, and deprotonation and alkylation step can formulate this, right? And one more step, right? Deprotonation and alkylation can give you this internal alkyne. And then hydrogenation using lindolar catalyst can give you cis-selected olefin alkene, and then MCPBA epoxidation will give you a final product. So this is how you can design the synthesis via retrosynthetic analysis and propose the full synthetic pathways. 그래서 이제 반응 라이브러리가 정리가 잘 되어 있으시고 연습이 좀 되어 있으면 주어진 스타팅 머티리얼로부터 타겟 프로덕트를 합성할 수 있는 경로를 제한하실 수 있겠죠. 근데 합성 경로를 제한할 때 중요한 점은 여러 가지 프로덕트가 나올 수 있는 것 중에 하나만이라도 된다면 이거 오케이다가 아니라 그것만 만들 수 있어야 되는 거죠. 그래서 반응의 선택성이나 메커니즘 등등 잘 알고 계시면 좋겠죠. 예를 들어서 시스 프로덕트를 만들어야 되는데 트랜스 프로덕트를 만드는 리덕션 조건을 선택했다. 그러면 합성이 안 되겠죠. 그렇죠? 그런 경우에 점수를 받을 수가 없습니다. 그래서 반응, 선택성 그리고 메커니즘 등을 좀 파악을 하고 계시면 되겠죠. Right. What about this one? 3,3 dibromohexane. This is a germinal dihalide. So you can recall some reaction, right? We discussed about the product in this form in our kind chapter. And here's a condition. You need to use a reagent with no more than 2 carbons, right? And this is the retrosynthetic and synthetic pathway, right? So to make this germinal dihalide, you can think of alkyne, right? So if you add excess HX, in this case HBr, then the addition of HBr twice can give you a germinal, right, dihalide. This is what we studied in our alkyne chapter, the very first reaction we covered. Right? And to make this internal alkyne, you can also think of the terminal alkyne in this series. Then applying base and alkylation condition twice can give you this internal alkyne, the same pathway we discussed in the previous slide. Right? And after making this internal alkyne, you can add HBr twice, and this will give you selectively germinal dihalide. We discussed why germinal dihalide is given with high selectivity in this case. I guess this is the last example. How can you make this aldehyde, COH functionalities, from this substrate? Right? And this is a retrosynthetic analysis, right? This aldehyde functionalities can be made from the oxidative cleavage. If you recall, the organolysis, in other words, right? Then you can use this internal alkene, right? And then if you treat ozone and perform the organolysis, the oxidative cleavage process, and you recall, right? Then double bond, CC double bond will be cleaved and give you CO double bond in between, right? That's what you want, right? That's the target product. And to make this alkene, you can think of alkyne and running hydrogenation reaction, and that will give you the alkene. And then you need to use the Lindelar catalyst too, right? Because you want to stop the reaction at alkene stage. And to make this internal alkyne, of course, same thing. You can make, right? You can perform deprotonation and alkylation step. So from the starting material, deprotonation and alkylation will give you internal alkyne, Lindelar catalyst, right? Hydrogenation reaction with Lindelar catalyst will give you alkene, and ozonolysis will give you oxidative product, right? That you want for this problem. Okay. All right. I guess that's all for alkyne chapter. Again, you need to remember and understand the reaction mechanism of the varieties of the addition type reaction we covered across alkene and alkyne chapter. Then you can propose the synthetic pathway for a given product from given reactant or reagent. Okay. All right, let's move on to new chapter 8, where we study about the delocalization of the electron, right? And aromaticity and electron effects as well. And we'll cover up the addition type reaction in this chapter as well with the delocalized alkene or delocalized electrons. Okay. So what is the delocalization or delocalized electron versus localized electron? So thus far, all the nucleophile we studied thus far, basically the localized electrons, right? For instance, this amine has the localized electrons, okay? Here's a lone pair, belongs to the nitrogen atom, right? The atomic site. Or there's a pi electron, right? In double bond. This is also localized electron. Of course, you have a localized electron formulating a single bond, right? So these electrons are all localized. Right? Localized electrons belong to a single atom or shared by two atoms. Right? So this lone pair localized a single atom, right, on nitrogen, and these pi electrons are shared by two carbons, and also the bonding electron. These electrons are also shared by two atoms, right? In between carbon and nitrogen in this case between two carbons. But these are all localized. What about delocalized electrons, right? Delocalized electrons are usually shared by three or more atoms, right? So this is typical examples of the delocalized electron and functionalities. We'll study a lot in this chapter, right? So diene, we discussed about the structure of diene in the arcane chapter, and you know how to call out, right? We studied about the nomenclature of diene, right? In this case, the electrons are shared by the multiple atoms, right? We'll study a lot about that. And you can compare, right? Maybe left-hand side molecule versus right-hand side molecule, right, and down below. In this case, again, double bonds are separated by one single bond, right? In this case, the pi electrons cross four different carbons, they can be delocalized. But if you have one sp3 hybridized carbon in between, then this will block the delocalization of the pi electron cross, right? So these pi electrons are basically localized within these two carbon, right? And again, these pi electrons are also localized on this carbon-carbon side, right? So in this case, electrons are all localized, right? But again, in this case, electron can be delocalized across four different pi bonds, four different carbon atoms, in other words. And a typical example of delocalized electron, right, in a system, right, the molecular system, it's a well-known example is the benzene, right? You know how benzene looks like. The molecular formula is given like this, 6686, right? And then you can calculate the U, right, degree of unsaturation, what is if the molecule is fully saturated, then you have to have 14 hydrogen, but instead you have 6, right, in benzene case. So 8 divided by 2 will give you 4 as a DU, right? So with these magnitudes of DU, you can propose structure of the benzene. Right? And this is another example, sorry, the information you can take into account, right? When people run the reaction, right, with benzene and try to replace one hydrogen with the other substituent, and this is denoted as X. When one hydrogen is replaced with X, we found only one monosubstitute compound. But when one additional hydrogen is replaced with X, right, then that will give you 3 different products. So combining all this informations, people try to propose the correct structure of the benzene. And these are 2 possibilities, right? And if you can consider, right, the U of 4, you have 2 triple bonds, right? That each constitute DU of 2. So in total, this will satisfy DU of 4, right? What about the right-hand side structure? You have 3 double bonds, right? Will constitute DU of 3, and 1 additional ring structure that will give you DU of 4 as well. And these are possibilities, right? And with this ring structure, right, you can think of them as alternated, right, shorter and longer bond between carbon, right, and carbon. These three double bond containing carbon to carbon distance must be shorter than these carbon and these carbon and this carbon bonds. So this is the initial proposal in the early days, and combining the information, additional information I addressed, right? Replace one hydrogen with X, and additional, right, placement of hydrogen with X. For each step, for the first step, you get only one monosubstitute product. In the second step, you get 3 disubstitute compound. So that's the key information you have to satisfy. But the compound 1, this, right, linear arc compound, cannot satisfy, right, this condition. Compound 1 from 2 disubstitute product. So you can rule out the compound 1 and compound 2. Still, right, cannot satisfy compound 2 actually formulate 4 disubstituted compound, right? If, right, this structure is right, then these 1, 2 disubstitute products have to be different, right? Because there's a distance difference here and there, and also, right, the bonding character is different. In this case, you have double bond, and here you have single bond. So in this structure, if this structure is right, then these 2 have to be different. Right? And then Kepler, you probably heard, right, their proposal in early days with the structure of benzene to rationalize this discrepancy. Right? And he proposed like benzene is sort of like mixture of 2 compounds, and there exists a rapid equilibrium, right, between shorter and longer carbon. And if this is right, then maybe you can treat these 2 are basically in rapid equilibrium, and you may get only 3 products, right? Because these 2 and these 2, and these 2 structures are in an equilibrium, so you can count as a 1. That was the initial proposal made by Kepler. Right? And people confirm the cyclic structure later on, right? In now 1910, people report this reaction. Until then, people didn't know the correct structure about benzene. But when they run this reaction, the hydrogenation reaction using nickel catalyst, at this reaction, under this reaction condition, they got cyclohexane. So from this, people make a confirmation. Benzene must be a cyclic structure. And later on, right, with the development of these spectroscopic tools and diffraction technique, people get the idea of the structure of the benzene. Right? And all the carbon bond in benzene found to have the same length scale. Right? And they are longer than, right, the bonds are longer than double bonds, but shorter than single bonds. Right? That's what people characterize about structure of the benzene. And finally, right, people found the way to represent the structure of the benzene, showing the delocalized electron. So you can, using this dot notation indicating, right, all bonds within this, right, benzene structure, carbon to carbon bonds are equal, right, and same lengths, and they are shorter than single bond, but longer than double bonds, right? Or you can simply put a circle inside, and this represents the delocalization of the electron across 6 carbons, right? So these structures show that pi electrons are fully delocalized, but they do not share. They do not show the number of the pi electrons still, right? But you can count the number of pi electrons, right, with the framework made these days. And you can think of, right, the resonance contributors for presenting the resonance hybrid in benzene structure. And this is not the equilibrium though, right? This is the resonance. Resonance and equilibriums are completely different one. Okay? So only proposal of them calculate is not rigorously true, right? The concept of resonance is again different from the equilibrium. Right? So to make this resonance hybrid, you have a contributors, right? One contributor and contributor two. Okay? And these are equally contribute to make this hybrid structure. Okay? 그래서 저 화살표 표시를 이퀄리브리엄 표시로 오해하는 경우가 있습니다. 이퀄리브리엄과 완전히 다른 컨셉이에요. 그래서 벤젠의 구조를 먼저 그린다. 정확한 구조라고 했을 때 레조넌스 컨트리뷰터 1도 그리고 레조넌스 컨트리뷰터 2도 벤젠의 스트럭처를 프레젠트하지 않습니다. 두 개의 하이브리드가 정확한 표기예요. 두 개가 이퀄리브리엄 상태에 있다. 그 개념이 아니라 이 레조넌스 하이브리드를 이루기 위해서 구조적 컨트리뷰터 1, 구조적 컨트리뷰터 2가 존재한다. 이렇게 이해를 하셔야 돼요. 그렇죠? Right, that was a typical example of the delocalization in delocalized system, right? The benzene molecule. What about cyclooctatetraene, right? So you can draw, you have a structure here, right? And you can think of like the p overlap, and for maximum p overlap, the atoms that share the delocalized electron, they must lie in the same plane. So if you go back to your benzene, right, we didn't cover up the location of the pi or p orbitals and pi electrons, right? So you know, right, all the carbon within benzene, they are sp2 hybridized, right? They have 3 arms. That means you have one remnant p orbitals for each carbon, right? And these locate perpendicular to the plane of the 6-member ring, right? And like figure in B, right? And this p orbital, right? They can formulate this, right? Bonding interaction, right? And electron, pi electrons basically can delocalize across, right, this orbital set. And this is the electrostatic potential map of the benzene. So we'll study a lot about delocalization, and in a few slides later, so basically delocalization can take place across p orbital sets. Okay? Yeah. What about cyclooctatetraene, right? You can think of like getting the p orbital overlap in the system, and to gain, right, the full overlap, they have to formulate the same plane. They must lie in the same plane. If you take a look at the structure of the cyclooctatetraene, actually they cannot formulate the single plane, right? There's a sort of like the band structure, right? And if you draw the p orbital, right, then you can then rationalize why, right, the p orbital overlap cannot be fully gained in this system. You can maybe expect the overlap of this blue lobe in p orbitals, but these green, right, they are located quite far away to each other, so they cannot interact, right? They cannot overlap basically. So you can identify them sort of like delocalization of the localization of the electron, relatively speaking, right? The cyclooctatetraene is not completely planar, so it does not have a localized electron, rather you have somewhat localized electron here and there, right? It's unlike benzene, which has full delocalization. You can think of like nitrate or carbonate system, where delocalization electron can take place across 3 different atoms, in this case oxygen, 2 oxygen and nitrogen, right? And you can draw the resonance structure or resonance contributor of the nitrate system, right? And these two are possible resonance contributors, right? You can draw, right, two resonance contributors from one to the other, right? And as I mentioned earlier, the localized electron, they result from p orbital of one atom lapping the p orbitals of two adjacent atoms, right? And you can check the degree of hybridization across three different atoms in this particular case. You know that this oxygen is sp2 hybridized. This nitrogen is also sp2 hybridized, right? We have three arms. There's no lone pair, right? So you can count 1, 2, 3 arms. The central nitrogen is sp2 hybridized for that reason, and you have another oxygen there, which is also the sp2 hybridized, right? So they must have then, right, the p orbital for each, and that p orbital, three different p orbitals, they can communicate and formulate the localization system. Right? You can make the overlap. Okay? And these are general rules. Okay? Rules for drawing the resonant contributors. So following these rules, right, you have to practice, right? You have to practice across many examples possible. Right? So there are 4 rules. The rule number 1, for drawing the resonant contributors, only electron move. Right? You shouldn't touch the location of the atoms. Right? See, atoms never move. That's the rule number 1. And rule number 2, only pi electrons. Okay? In other words, electrons in pi bonds, okay? And lone pair electrons can move. Sigma electrons, or in other words, electron and sigma bond, they never move. Okay? So you cannot touch the skeleton, right? Skeleton of your molecule. Right? Gain only pi electrons, and lone pairs they can move. Okay? So pi systems, or electron and pi system, they only move. Okay? Rule number 3, the total number of electrons, of course, does not change. Right? You cannot change the total number of electrons. Rule number 4, electron always move to an sp2 or sp atoms, because only these atoms, right, accommodate p orbital. Right? sp3 atoms cannot accept electrons, right? There's no p orbital, right, in sp3 hybridized atoms, right? So that's also a very important rule. Right? Electrons always move to an sp2 or sp atom. This is example, right? Example of the resonance. So you have double bond here, and you have positive charge on this, right? The allylic carbon. Right? And then you can think of like the hybridization and location of the double bonds, right? So because you have double bonds here, you can imagine there is a p orbitals. And of course, these two carbons are sp2 hybridized, right? What about this carbon, right? This is a carbocation, and again, this carbocation only has 3 arms. Right? So this carbon is also the sp2 hybridized. Right? That means there's remnant p orbitals because you have positive charge on this carbon. Right? So all p orbitals, right, across 3 different carbons, they can communicate in this systems. Right? But applying the rule that we just covered in the previous slide, right, you can draw the second resonant contributors. Right? Movement of the pi electron in this pi bonds can move to, right, the sp2 carbon, or in other words, p orbitals, right, in this sp2 carbon. Right? Then you can formulate this new double bond in the second resonant contributors, and positive charge will remain on, right, the carbon next to it. Right? And these two will formulate the resonance hybrid. And for drawing the resonance hybrid, you can designate or represent the partial bonding character. Right? You can basically mix these two resonant contributors. Right? And you can pinpoint the atoms that has the delta plus, right? So this carbon has a plus. That's why you have to draw the delta plus on this carbon. And also this carbon has a plus charge, right? The second contributors, so that you can represent the delta plus in the resonance type. Okay? And from the resonance contributors, right, 1 and 2, you know that there is a partial double bond character on the left-hand side. Okay? And from resonance 1 and 2, for the second and third carbon, you can also rationalize this bond as to be a partial double bond character. So you can use single and dot notation. Again, electrons cannot move to sp3 carbon because sp3 carbon doesn't have p orbital, and also sp3 carbon basically has a complete octet, so they cannot accept the electron, right? So this example, right? So you have double bond here again, right? And then you have to think about the carbon next to it, right? But this carbon, unlike the other case, right? It's an sp3 hybridized, right? It has 4 different arms, right? There are 2 bonds, right, between other carbons, and also have 2 CH bonds. But there are 4 different arms. This carbon is sp3 hybridized. No p orbital cannot accept the electron from the pi electron, the left-hand side, right? So in this case, this double bond cannot be delocalized. It has to be isolated or localized within the double bond. Okay, so there will be no resonance contributors for that. Another example, again, you have double bond here, and another sp2 carbon, the power cation site. So then you can imagine, right, movement of the pi electrons. Then after this movement, right, this carbon will have positive charge. Okay? And then you have another double bond on the left-hand side, and this can, the pi electron thereat can move to, right, the sp2 hybridized carbon, or in other words, p orbital set, right? And then after all, right, the right-hand side, you can create the third resonance contributors, right? Positive charge remaining on this carbon, right? Then combining this, right, 3 resonance contributors, you should be able to draw a resonance hybrid, right? Reflecting all this, right, 3 information. So you have positive charge on this carbon, and this carbon, right? So you have to designate delta plus, right, on each carbon as well, right? And considering the double bond character, you can draw the partial double bond character across all carbons, right? 그래서 레조넌스 구조 그리는 것도 유기화학에 있어서 중요하죠. 그래서 저희가 레조넌스를 그리는 이제 원칙, 룰에 대해서 4가지를 다뤘고, 원리를 알면 직접 외울 필요가 없습니다. 그렇죠? p 오비탈이 이제 오버랩이 중요한 거고, 파 일렉트론이 이제 편저되는 거. 시그마 본딩을 형성하고 일렉트론을 건드리는 게 아닙니다. 이거는 싱글 본딩을 형성하고 있고, 레조넌스 구조에서 애톰이 움직이는 것이 아니라 일렉트론이 비편져야 되는 것이기 때문에 파 일렉트론이 관여되는 것이다. 그 원리를 알고 계시면 앞에서 다룬 룰 넘버 1, 2, 3, 4가 다 make sense 해지겠죠. 그죠? 그래서 이해를 하신 다음에 example을 여러 개 풀어보시면 이제 익숙해질 거예요. 그죠? Okay, what about the lone pair, right? Lone pair also can move. So this is the ni, and you can also think about the degree of hybridization in the central atoms, right? In this case, for example, this carbon has 3 different arms, right? So it's sp2 hybridized. That means this carbon also has remnant p orbitals, right? Perpendicular to this plane, right? And then you have the lone pair from nitrogen. Nitrogen sitting next to the central carbon, right? And then this lone pair can participate in, right, the bond between this carbon, right, to formulate the double bond there. And as a result, nitrogen will have the positive charge because it's donate, right, the electron density to formulate the double bonds. And at the same time, there's a movement of the pi electron, right? Initially, formulating the double bond between carbon and oxygen, right? And this will create the delta negative charge on this resin hybrid. Right? You have O minus and the second contributors. And combine these two, right? Resin contributor 1 and 2, you can draw this resonance hybrid. Okay? Delta plus sitting on the nitrogen, right, from the second contributors, and delta minus also sitting on the oxygen, right, from the second contributors. And from double bond and single bond occurring between carbon and oxygen, and also the double bond and single bond occurring between nitrogen and carbon can represent this partial double bond notation, right? Single bond with dot 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 notation, right? What about this case, right? Again, you have sp2 hybridized carbon in between, right? So this cannot accept the lone pair or pi electron, in this case, the lone pair, right? Because this sp3 carbon is already fully saturated, right? There is no p orbital, right, on this sp3 hybridized hydrogen site. But this site, the carbon cannot accept the electron. So this lone pair is fully localized on the hydrogen site. Another example, movement of the pi electron to sp carbon. Right? sp carbon, of course, right, have remnant p orbital, right? So you can accept the movement of the pi electron from double bond or triple bond sitting next to it, right? So you have, for instance, like double bond here, and you have sp hybridized carbon, which has remnant p orbital. Sorry, which has this p orbital. In this case, there is no charge, right? So this can accept the movement of the pi electron, right? So you can draw the arrow like this, right? And after all, you can have the double bond here, right? Basically, the pi electron formulating the double bond on the left-hand side and 1 and 2 carbon, right? That pi electron moves to the central position to formulate the double bond between 2 and 3 carbon in this case, right? And as a result, right, the ended carbon, number 1 carbon, get positive charge, right? And the movement of the pi electron between carbon and nitrogen, right, will formulate the negative charge on the other end, nitrogen. Combining these two, contributor 1 and 2, you should be able to draw the resonance hybrid. The delta plus on this carbon from second contributors, delta minus from second contributors as well, and you have to draw the partial bonding notation. In this case, you have, right, partial double bond resonant contributors from resonant contributor 1, and single bond from resonant contributors 2. And what about the middle one? You have single bond from 1 and double bond from 2. That's why you have, right, the partial double bond. What about the bond between carbon and nitrogen? You have triple bond from the contributor 1 and double bond from contributor 2. So mixing these two, you will have perhaps the bonding order in between the double and triple, right, in between carbon and nitrogen. And that's how you can designate the bonding nature. So this is the protein structure and peptide bond, right? They can have the delocalization, right? Find what we studied in this slide, right? And delocalization, the electron delocalization influence the protein structure, right? So you can basically think of like there's a partial double bond character in between carbon and nitrogen from, right, this resonance effects, right? And there are lots of ni bond, right, in protein. So delocalization definitely affects a lot about the structure of the protein, right? All right, so I guess now you can draw the resonance contributor, right, or resonance structure. But perhaps you can think of like which contributor has a higher priority or higher contribution to the resonance hybrid. Right? So let's say you have two possible resonant contributors, right? A and B in this case, for a given carboxylic acid. Which one contribution is larger? Right? You can think of right degree of contribution from each contributors to resonance hybrid. Right? So comparing A and B here, you can tell A has a greater predicted stability, thus contribution to resonance hybrid than B, right? So this is one contributors, right? And after right movement of pi electron, you can draw the second resonant contributors with given the charge separation, right? In this case, you can tell A has a greater contribution or greater predicted stabilities. We'll discuss about the stability versus degree of contribution right, in a few slide later. But this one, A, has a higher contribution or greater stability because B in this case has a separate charge, right? But A has a neutral. So neutral means right separate charge. That's one general trend. And what about this one, comparing C and D in carboxylate, right? Unlike carboxylic acid, you start from the carboxylate anion. So basically these two are identical, right? In this case, right, C and D have an equal predicted stability. Of course, you should be able to draw right, the second resonance contributor from right, C, right? You should be able to draw D from C or C from D, okay? In this case, these two structures are identical, so this will have equal contribution to the resonant contributors. What about E versus F, right? You have, right, the double bonds and also the ketone structure, right? And since this carbon is sp2 hybridized, right, you should be able to draw the second resonant contributors F, right? From E, you can draw the movement of the pi electron and also movement of the pi electron, right? So from E, you should be able to draw F, right? And after right movement of the pi electron, this carbon will have positive charge, whereas this oxygen will have negative charge, right? If you take a look at right this carbon has an incomplete octet, right? So if you have to compare right stability E versus F, E has a greater stability, okay? And thus E will contribute more to the resonance hybrid, right? So whether the atom complete or having incomplete octet is also very important criteria, okay? What about G versus H, right? So you have double bonds and also the oxygen, right, next to the double bond carbon, right? And then right, you have lone pair, right, and oxygen. And this lone pair can also move, right? So you can draw the resonant contributors H, right? The resonant structure H, right, from G. And after movement of the pi electron and lone pair, this oxygen will have plus, right? Forward charge, and this carbon will have negative forward charge, right? +1, -1. In this case, right, charge are separated, right? In H compared to G. In G, there's no forward, right? There's no right charge separation, but also, right, if you think about the location of the positive charge, right? It's reside on the oxygen, right? Oxygen is electronegative atom, right? It's not happy with having plus charge, right? So that's one other consideration, right? H has a positive charge on electronegative atom, which is not happy, which is not good. So in this case, G has a greater stability and greater contribution to resonance hybrid, okay? What about I versus J? Right? Again, you have double bond, right, or sp2 hybridized carbon, and you have carbon anion next to it, right? And this lone pair can move to formulate the second resonant contributors, right? You can draw the root node of the electron, right, in this series. And then you can propose, right, the double bond between these two carbon and O minus, right, movement of the pi electron, right? But if you have to compare, right, I versus J, right, you have minus charge, right, on carbon and I, right, and on J you have negative charge on oxygen. In this case, right, the right hand side is more preferable, because you have negative charge on more electronegative, right, ions. Compared to carbon, oxygen, relatively speaking, have here to accommodate minus charge. Right? That's why J has a greater stability, greater contribution to resonance hybrid than I. Okay. So these are the summary, the features that decrease, right, the predicted stabilities and degree of contribution to resonance hybrid in other words, right? So one, atom with the incomplete pad, this is not good. Two, negative charge that is not on the most electronegative atom, that's what we discussed, right, in the previous slide. Three, positive charge that is on an electronegative atom, right? O plus, for instance, is not good. And four, separate charge. Okay, so compared to separate charge, neutral system is better. Okay? So these are the features that you should remember, right? You want to compare the degree of contribution from two or multiple resonant contributors, okay, to resonance hybrid. 그래서 뭐 파이 일렉트론, 뭐 lone pair 움직여가면서 저희가 resonance structure를 여러 개 그릴 수가 있겠죠. resonance hybrid에서는 저희가 뭐 dot notation 그리고 뭐 positive, minus charge location을 이제 pinpoint해서 그릴 수 있지만 경중을 비교하지는 않죠. 그죠? resonance contributor들 중에 경중이 있다는 이야기이고 그 경중을 이제 판별 혹은 따질 수 있는 기준을 여기 1, 2, 3, 4로 제시하고 있는 거예요. 그래서 다 뭐 resonance structure 가능하다고 해서 다 같은 정도로 resonance hybrid에 기여를 하는 게 아니라 기여하는 정도가 다릅니다. 그리고 기여하는 정도가 뒤에서도 다루겠지만 비슷할수록 delocalization, stabilization 에너지의 크기가 또 결정이 되게 돼요. 아무래도 resonance contributor의 기여도가 비슷할수록 delocalization 되는 정도가 커지겠죠. 그렇죠? 하나가 만약에 독단적으로 너무 유리한 구조다. 그러면은 그 구조가 resonance hybrid의 대부분을 대표하는 스트럭처가 될 것이고 그만큼 그 스트럭처 하나에만 전자 구조가 결정이 되겠죠. 그렇죠? 그래서 애톰인데 incomplete 옥텟이다. 옥텟 룰을 만족 못하는 애톰이 있다. 그럼 일단 그 resonance structure는 해피하지 않는 거예요. 그렇죠? 2번 네거티브 차지가 일렉트로네거티브는 아톰에 놓여있지 않아. resonance 뭐 contributor A, B를 만약에 비교한다. 그래서 많이 다뤘지만 이미 뭐 그 경우에 네거티브 차지가 일렉트로네거티비티가 높은 아톰에 놓여있지 않아요. 그러면은 그거 가지고 판별할 수가 있다. 심지어 일렉트로네거티브 애톰에 포지티브 차지가 부여되는 경우도 있겠죠. 그 경우도 해피하지 않다. 그리고 separate charge냐, neutral case냐. 만약에 두 개를 비교해야 된다면 neutral case가 좋다. 그렇죠? 기억하시면 되겠습니다. Okay, that was just kind of like summary features that decrease predicted stabilities and eventually, right, degree of contribution to the resonance hybrid. And here you can think about like delocalization. So thus far we discussed about the idea of the delocalization electron within a molecule. And you can think of like energy-wise, right? Like delocalization is good for the molecular system. The delocalization energy is defined as the extra stability that a given compound has as a result of having delocalization, right? To delocalize electron, in other words. Right? And electron delocalization is also called the resonance. That's delocalizing energy. It's also collapse of resonance energy. So basically same thing. Okay? Electron delocalization, resonance, basically same thing. That's delocalization energy and resonance energy. These two terms are essentially the same thing. And from this, right, you can then guess the resonance hybrid, right, has to be more stable than any of its contributors. Right? So if electron get delocalized, the system can have a benefit, can have an additional stabilization effects, right, for delocalization energy. Okay? 그래서 일렉트론이 비편저하가 된다. 편제화가 아니라 비편제화가 됐을 때 그 분자가 가질 수 있는 이득이 있다라는 거고요. 그게 이제 안정화 효과로 에너지 효과로 이제 얻어지는 거다. 이렇게 이해를 하시면 되겠습니다. 왜 그러냐? 그거는 뭐 저희가 delocalization, localization 효과 뭐 다른 챕터에서도 조금 다루긴 했었어요, 사실. 일렉트론이 넓은 공간에 퍼져 있는 게 기본적으로 더 좋습니다. 일렉트론이 좁은 공간에 갇혀 있는 것보다는 넓은 공간에 있으면 일렉트론끼리의 이제 뭐 일렉트로스태틱 관점에서 간단하게만 생각해봐도 아마 rationalization 될 수 있을 거예요. 그렇죠? delocalize 된다라는 말은 일렉트론이 넓은 애토믹 스페이스에 퍼질 수 있다는 것이고 그만큼 안정화가 되는 거겠죠. 쉽게 생각을 해볼 수도 있겠습니다. 그리고 delocalization 효과로 얻어지는 이 부가적인 안정화 효과를 저희가 delocalization energy라는 텀으로 이제 수치화할 수도 있을 것이고 다른 말로는 resonance energy라고 저희가 정량을 해볼 수도 있겠죠. 그러면은 resonance contributor 뭐 A, B, C, 뭐 A, B 이렇게 있는 경우에 저희가 resonance hybrid 구조를 그릴 수가 있었잖아요, 그렇죠? 그러면 그 resonance hybrid 실체와 이제 각각의 컨트리뷰터들의 에너지를 또 비교해 보면 하이브리드가 당연히 에너지적으로 더 안정한 구조라는 거죠. 컨트리뷰터는 하나의 구조를 표현할 뿐이고 가능한 구조를 하이브리드는 그 구조 여러 개가 구성하고 있는 delocalization 된 구조를 전체적으로 표현하는 구조이기 때문에 당연히 delocalization 에너지만큼 안정화 효과를 누리겠죠. 그렇죠? Okay, so these are again, this is the definition of the delocalization energy, and then you can now think of then, right, the energy standpoint. You can compare, right, the stability of the resonance and hybrid, and also resonance contributors. Right? So this is a rule, right? To sum the stability of a given resonance hybrid and resonance contributors, right? So greater number of relatively stable resonance contributors, right? You will get the greater delocalization energy, right? So comparing this left-hand side versus right-hand side, you can discern the magnitude of the delocalization energy or resonance energy, right? So this is the carboxylic acid case, right, as we discussed in the previous slide. Right-hand side is the carboxylate anion case, right? In this case, right, you have separate charge. In this case, neutral, right? So you can tell, right, the left-hand side resonance contributors is more stable, right? Than charge separate case, okay? And you have also the positive charge on oxygen, which is not happy, right? So this one is more stable than the charge separated one, right? What about the right-hand side, the carboxylate? There's a different species, right? In this case, you have equal, right, contribution from this equal contributor, right? Contributor 1 and 2, they are basically equal, right? And these two are both relatively stable, right? But again, in the left-hand side, you have more stable resonance contributors, right? So these two have different energy, whereas these two have almost identical energy, right? In this case, right, you will get more or greater delocalization energy. So carboxylate anion, right, will have greater delocalization energy, resonance energy, in other words, than the left-hand side, the neutral carboxylic acid case. Right? The greater the number of relative stable resonance contributors and more, right, nearly equivalent their structure, the resonance energy will increase, right? Greater the rate of energy networks. So you can compare, right, the first case versus, right, the bottom cases, right? So you have the dyne again, and you can draw the resonance contributor left hand side and right hand side, right? And left hand side and right hand side, you have the separate charge and also the incomplete path, right, on carbon, right here as well. So in this case, you have a distinctly more stable resonance contributors, right? The central form compared to the left and right hand side. Basically, you have only one relatively stable resonance contributors, from which you can expect there will be very little delocalization or delocalization energy you will get. Right? So if you think about, right, the resonance hybrid from these three different resonance contributors, of course, the center form will dominate, right, the degree to which formulate the resonance hybrid. Right? There will be no or very small delocalization energy. What about the bottom case? You have DO3, 2 minus, right, carbonate anion, right? In this case, basically, three different resonance contributors can be drawn, and they are structurally and energetically identical, right? So you can expect then significant delocalization or resonance energy from these nearly identical, basically in this case, identical, right? Three contributors. Right? What about benzene? As we studied in earlier today, right? You have two identical resonance contributors, right? So in this case, you can expect gaining significant delocalization or delocalization energy. Right? Basically, you have two equivalent, two identical resonance contributors. Right? 그래서 결국 레저넌스 컨트리뷰터의 구조가 비슷하고 스테빌리티가 비슷할수록 레저넌스 하이브리드를 이루는데 이퀄 컨트리뷰션을 줄 가능성이 높아지겠죠. 그럴수록 레저넌스 에너지가 커진다는 이야기예요. 디로컬라이제이션이 더 많이 일어나겠죠. 그렇죠? Right? So this is our summary. The greater the predicted stability of the resonance contributor, more it contributes to the resonance hybrid. This is very logical, right? And then the greater the number of relatively stable resonance contributors, greater the delocalization energy, the more nearly equivalent the resonance contributors, greater the delocalization energy as well, okay? All right, that was about the basics about delocalization, right, and resonance structure. And then can come back to the conjugated dyne, right? And we'll learn about its reaction a lot in this chapter. Okay. So again, you can discern the left-hand side cases as isolated dyne, right? There's sp3 hybridized carbon in between. So these two pi electron system, pi electron in these two double bonds, they cannot communicate, right? They are blocked by this sp3 hybridized carbon in between. But in this case, you don't have such a blocker, right? These pi electron and these pi electron, they can communicate, right? They can, in other words, be delocalized, right? Double bonds are separated by, in this case, one single bond, right? So in this case, you can say it's conjugated dyne. They can conjugate, right? But in this case, isolate. Okay? And this will this leads to the energy of the system too. Maybe you can compare 1,4 pentadiene. You have double bond here and there, and in between you have again sp3 hybridized carbon. So they are isolated double bonds, right? Whereas 1,3 pentadiene, they have same number of carbon and all hydrogens too, but they have different location of the double bonds. Right? In this case, these two double bonds are conjugated. Right? There's no blocker in between. Right? And you can imagine, right, running the same hydrogenation reaction, and this will give you same arcane product. Right? So product states are same, but you can measure the heat of hydrogenation reaction by experiments and compare the magnitude of that. Right? As a result, the above one, the 1,4 pentadiene, give you a higher number, right? And then the 1,3 pentadiene as a lower number. What this number means, right? This number basically indicates the stability of the system. So 1,3-pentadiene reside lower in energy as compared to pentadiene. So the product, right, it's basically identical, right? So you can then think of like how high line the reacting state, right? So after hydrogenation reaction, you can get, right, the delta H or heat of hydrogenation in the opposite sign. Right? So this number telling you that 1,4-pentadiene is sitting about that 1,3-pentadiene. Right? So conjugate diene, in other words, is more stable, right? Because of the conjugation effect, or in other words, the resonance effects. Right? So conjugate diene is more stable than isolated diene. Okay. And as we studied, right, conjugate diene have delocalized electrons. Okay. So you can draw, right, from this major resonance contributors, you can draw two different resonance contributors, right? Following the blue arrow to left hand side, right? And following the red arrow to right hand side, you can draw two different, right? Two additional resonance contributors, and combining all these three, you can draw the resonance hybrid, right? And from this notation, you can rationalize how pi electrons are delocalized across 4 different carbon, right? So 1,3-butadiene have delocalized electrons. And you can think of like the bonding character, sp2-sp2 bond, right, is stronger, right? So if you think about the bond between this carbon and this carbon, right? And each carbon, left hand side and right hand side, both they are sp2 hybridized, then you can perhaps, right, identify the bonding character between two, so sp2 and sp2, right, overlap. What about the bond between here, right, this carbon and this carbon? This carbon is again sp2, this carbon is sp3 hybridized, right? This carbon is also sp2 hybridized. So this bond and this bond, they can describe as a single bond formulated by the sp3 and sp2 overlap. And then if you think about the S character, you can tell, right, sp2 overlap, right, will give you a stronger bond, right? And stronger bonds also give rise to a compound with higher stabilities, right? So stronger bond causes compound to be more stable. And that's why 1,3-pentadiene, as we discussed on this slide, right, it's a low line energy, or in other words, more stable than 1,4-pentadiene. Right? That's one other rationale. And this is a generalized, right, table. Carbon-carbon bond lengths and strengths depends on hybridization. Perhaps as you already know, in this case you have sp3, right, communication. In this case sp2, sp3, sp2, sp2, right, sp3 and sp, right. In this case you have sp and also sp2, right, and you have sp and sp, right? And following, right, the degree of hybridization larger, right, the S character, right, bond lengths will decrease, right, and give you higher stabilization. So you can think of like degree of S character in this bonding interaction. Okay? And this is a typical case, the exemplar molecule, right, showing the accumulated double bonds. Right? This type of compound is called allene, right? And allene, right, has central sp hybridized orbitals, and central sp hybridized orbitals have 2 perpendicular p orbital sets, and each will formulate, right, the double bond or pi bond with the carbon next to it, left hand side and right hand side, right, highlighted in this deep green versus light green. Okay. 중간고사 때 비슷하게 나왔었죠, 그죠? 이 구조를 생각해서 그릴 수 있는 게 포인트였습니다. 그렇죠? And also the configuration effects used in electronic device a lot So you can think of like polyacetylene, right, formulating from this, right, simple molecule, and then if you polymerize it, you can make this polymeric structure, which can conduct really well, and that's why this basic structure is used a lot in electronic devices, right? So conducting polymers can be used in many electronic devices, okay? And basically, electron can go through the pi systems. Okay? And allylic and benzylic site, right? So quite ubiquitous and very unique. And actually, this will give you the additional stability of the carbon cation. So this is called the allylic cation. You have double bond and carbon next to it, right? Have positive charge. And for the benzylic cation, you have the benzene ring and carbon next to the carbon, right? Having the positive charge. And we call out this position as a benzylic site and call out this site as an allylic site, right? And for each case, if positive charge residing on benzylic site or allylic site, we call out benzyl cation or allyl cation, okay? And since we know, right, this, right, can occupy the pi electron, right, from the left-hand side, and also the pi electron, right, from the left-hand side, you can draw the resonance structure or resonance contributors, right? So this positive charge can get stabilized really well from the movement of the pi electron left to it, right? The double bond and also the benzene, okay? So these show you very unique stabilities. So you can draw resonance contributors, right? Movement of the pi electron can allow you to draw the second contributors for the benzylic cation. Of course, you can draw multiple, right, resonant contributors, right? Because benzene ring can accommodate multiple resonant structure, right? So you should be able to draw all this, right, resonant contributors. And as a result of this resonance effects, the benzylic cation and allylic cation have unique stabilities, right? And you have like in upper length, right, in this stability series. So this is the stability series of the carbocations. So you already know these series, right? You know, tertiary carbocation, the arterial cation is more stable than secondary and primary carbocation, right? And compared to the tertiary carbocation, the allylic and benzylic cation is a higher stability, right? Because of this resonance effects, right? The positive charge can effectively stabilize with this resonance effects. Right? And within the allylic and benzyl cation, of course, right? If you have more R group, right, the stability will increase, right? In this case, tertiary allylic cation is more stable than secondary allylic cation, and of course, secondary allylic cation is more stable than simple allylic cation. Right? The same is true for the benzyl site. The tertiary benzylic cation is the most stable, more stable than secondary benzylic cation, and of course, secondary benzylic cation is more stable than simple benzylic cation. Okay? 네, 그래서 오늘 수업은 여기까지 하면 될 것 같은데 이제 결국 저희가 resonance conjugate 아이솔레이트 시스템 대비 비편줘야 되는 이제 알켄 시스템을 배웠고 비편줘야 되는 딜로클라이즈드 카이드렉트론 시스템이 어떤 가능성을 보이는지가 이 챕터의 핵심입니다. 그래서 이제 거기를 향해 가고 있는 것이고 다음 시간에 저희가 이해를 드리도록 하겠습니다.